Hello, OWASP Ottawa, and welcome to June. So, unless your car has a new sunroof and you're not still digging a tree out of your house, I assume because you're watching this that you have electricity. And so, welcome to the 21st century. My name is Garth. I am a co-lead at OWASP Ottawa, and I'm very happy to talk to you today and introduce our speaker this month. But before I do that, I want to talk about a few things about OWASP and OWASP Ottawa. OWASP Ottawa, or OWASP itself, is an international organization that's driven by members. So when you become a member, you get access to the community and a number of perks. And so OWASP will give you a number of things. I'm not going to list them all out here, but there's access to training, there's access to G Suite. You get to be able to move and vote on the OWASP board elections so you can influence the organization, and you can have access to that network of professionals and access to their jobs channel. There's a number of ways you can contact OWASP Ottawa. We have our Twitter, we have our own Slack, just because we started with Slack. You can follow us on LinkedIn, and obviously you're here on YouTube, so you've found us there. Our Slack has a jobs channel, so check that out for any jobs. As well as I want to shout out to our volunteers, Rick, Sharif, Adam, Scott, David, and well, I can't shout out myself. So you may be familiar with one of the keystone projects of OWASP Zap, and OWASP Zap needs your help, not only with contributing code, but also in sponsorship. So the links for Simon Bennett's GitHub sponsor page and Rick M's sponsor page are listed here, as well as a general blog talking about sponsorship. 2022 Global AppSec San Francisco has a call for papers, and the links are there. If you follow the OWASP Twitter, you'll be able to find the links there as well. But finally, I'm very, very pleased to introduce our speaker this evening, who's very patient because we had him planned last month before the storm hit, and he's been very patient and able to speak to us this evening on a topic of Kubernetes, managed Kubernetes security. And I don't know if you are aware of Kubernetes, if you worked in Kubernetes. If you're aware of and worked with Kubernetes and you're not scared, then you're not paying attention. So I'm really looking forward to this presentation. Amran has been Director of Security and Risk Management at a Vancouver-based firm called TaskTop, where he builds product security. He's building their product security program and advocating for a practical business-focused approach to security. He's also a board member of OWASP Vancouver. Shout out to Vancouver, as well as DC 604 DEF CON group. Welcome, Amran. I think you're on mute. That never happens.
Of course.
We're just testing your mic. Yeah, that's it.
Exactly. It's the phrase of 2021, right? You're on mute.
So hopefully I didn't slaughter your introduction too bad, but we're really, really looking forward to your presentation, and welcome virtually to Ottawa.
Thank you. Thank you.
Be careful where you park your truck.
I will need to buy one first. There we go. There's slides, so we can start. Hello, and thank you so much for having me. Today, we will be exploring how to secure managed Kubernetes clusters. As Garth said, my name is Emran Alavidze. I'm also known in the community as Erman. Today, I'm not representing TaskTop or PlanView. PlanView is the company that just bought TaskTop as official as of today. So everything I'm going to talk about today is my own opinion. This talk in practice is basically a consolidation of many months of learning, threat modeling, and incrementally improving security of our own production Kubernetes clusters. And I hope by sharing some of the tidbits and knowledge that I've gathered through this process, you'll be able to benefit from my experience as well. And we start with what is Kubernetes, and maybe we'll see if this works. But if you've ever worked with Kubernetes or know what it is, post some fancy emoji into the chat so I get a sense maybe how many people are there and how many people kind of listen, but also are able to post emojis. Kubernetes is open source container orchestration platform. It originated at Google. It's now a CNCF open source project, so it's maintained by a number of people, not just Google. It's designed from the ground up as loosely coupled collection of components that are centered around deployment, maintenance, and scaling of containerized workloads. It has a good support for declarative deployments. Basically, you define your desired state and then let the cluster do its work to basically get you to that desired state. And it has good support for immutable components. That's kind of a mouthful. So in practice, what this means is, to begin with, let's explore a little bit of terminology. So this is what a typical kind of Kubernetes deployment looks like. So we've got, in terms of terminology, the first thing we should talk about is the concept of pod. Pod is the smallest deployable unit of computing, basically smallest deployable unit of workload that you can create and manage in Kubernetes. In practice, what this means is pod is a running container, or actually it's a little bit more complicated than that, because pod can actually be several containers that basically work in the same namespace and can share information and network connections across each other. Containers, it's a common concept across like Docker and other containerization technologies. It's basically a self-contained application that you can run in Kubernetes as an example. So pods usually need some sort of configuration or secrets. In terms of Kubernetes, you can use external systems to inject those systems and secrets and configurations. But in terms of Kubernetes, it provides two concepts to do that. One is called config map, and that's used for, or it's intended to be used for configurations. That configuration can be injected into the container either as files. So think about, let's say, Nginx, and you want to create Nginx config file and inject it through using Kubernetes native tooling. So you will create a config map out of that file, and then basically the config map is mapped into your containers. The second concept is secrets, and secrets are actually very, very similar to config map. The big difference is most Kubernetes clusters support encryption of secrets at rest, and also by default they don't display secrets on screen. Even if you do commands like get secrets or list secrets, etc., the secrets themselves will not be displayed as plain text on the screen. But apart from that, they're fairly similar to config map. So again, you can mount those secrets as environment variables. You can mount those secrets as files, and basically that's how applications will use the secrets. So think about credentials and things like that the application or workloads might need to use. The next thing is deployments, and practically speaking, this is what you will deal with if you're running some applications in Kubernetes, because pods are not very useful because it's basically one container or a couple containers that run. If they you need to basically also tooling to support migration to new versions of those pods, support multiple instances of those pods, and support restarting those pods if they die or something happens to them. And this is what deployments are meant for. So deployment essentially describes those pods that will be running as deployment. It describes the number of replicas that you want of those pods. So you can be running 2, 5, 6, 7, 10, however many of those pods you want. And then you also specify the kind of the migration or rollout strategy. So if you update the deployment and specify a new version of that image, how that rollout is going to happen, whether it's going to deploy all new set of pods and then basically switch over, or whether it will do a rolling update with like potentially a mix of new and old pods versions running at the same time. The next important concept is a service. So service is a way, supposedly if you're running some application in Kubernetes, you will be exposing it to the outside world so that your users can connect and use the application. And this is done through service. Service is a Kubernetes object that allows you to specify how to publish the services and where to route them. And service, essentially underneath the service, takes care of the routing. So the service, Kubernetes knows where those pods are running, and when you connect to the service, it will automatically route the traffic to the right pods. So all of this relies on networking within the Kubernetes cluster. That networking is a pluggable thing, so it's not a native part of Kubernetes. You can run different network overlays or network plugins. They're called CNIs. And basically, essentially, in majority of the cases, at least the baseline is that everything that you run in the cluster can talk to each other. So there's sort of overlay networking throughout the cluster. Wherever your hosts are deployed, they will communicate each other and tunnel traffic so that the pods can talk to each other. So the hosts can be deployed in different regions, et cetera, but to the pods, to the workloads, it doesn't really matter. And the last important concept on this diagram is the concept of namespaces. Namespaces allow us to logically group related workloads together. And I'd like to highlight that this is logical grouping. There's no security boundaries, at least by default, in namespaces. So this allows you to kind of make the deployments more manageable in the sense that once you group those related resources, you kind of know everything that's related to that deployment. But also it allows you to, for example, to do things like run multiple applications. Maybe they're related, maybe they're not as related, but run multiple applications within the same cluster. As a side note, all of the services, Kubernetes control plane services, basically the system services that maintain and constitute the cluster, are also generally running in the same cluster in a special namespace called kube system. So if you want to, you can check kube system namespace and see all the different things that are running there that are part of the cluster. So I'm going to quickly check if there's been any questions. Looks like we're pretty good so far. All right, let's continue then. This diagram is from Kubernetes documentation, so you can just go online and check it out. I wanted to talk a little bit about what components, so the concepts that I've talked about just now, those are related to things that you run within the cluster, so things that we configure that are part of the application. This is how the Kubernetes cluster works. And at the core level, Kubernetes cluster consists of one or more master nodes, and master nodes are essentially running and maintaining this Kubernetes control plane. By the way, I'm not sure if you see my, yeah, you do. So I'm going to point with my mouse. So the Kubernetes control plane, this is those system services that essentially are the Kubernetes cluster, and the master nodes are responsible for running all of that and making sure they're available, et cetera, et cetera. And then there's worker nodes. So worker nodes are over here on this diagram, and worker nodes is basically the VMs or hosts where the workloads, the applications are actually being scheduled and executed and run. On the control plane, let's take a look at some of these components. So etcd is essentially a storage. So it's like a database that a Kubernetes cluster uses to store its state, the desired state, the current state, etc. So it's basically, it's the core storage of the whole cluster. It can be deployed within the cluster itself, or it can be deployed as an external cluster, as long as the Kube API server can connect to it. And as you can imagine, and we'll talk about this a little bit later, but anybody who has access to etcd, at least the right access, basically controls the cluster. So the next important component is the kube API server. This is the sort of the external interface of the cluster. This is what receives commands when you run kubectl and basically manages the whole thing. So this is how everything outside of the cluster interacts with the cluster. So if you need to do deployment, if you need to update the deployment or kill a pod or define a service, anything like that, anything to do with the cluster itself, with configuring and managing the cluster, is going to go through the API server. It's basically a relatively straightforward, although not complicated. Not complicated? It is complicated. But it's a REST API that essentially provides endpoints for like creating and managing Kubernetes objects that ultimately are stored in the etcd database. The next important piece is this kube controller manager, and we'll talk about what it does in just a bit. But essentially, it runs control processes in a loop, and those are the processes that help maintain the desired state. The next important component is the cloud controller manager. Kubernetes is often run in cloud infrastructure as a service providers. And Cloud Controller Manager is responsible for interaction of the Kubernetes cluster with that underlying cloud provider. So think about if I deploy a service in Kubernetes, I might tell the service that I want a load balancer in front of that server with some configuration of that load balancer, et cetera, et cetera. And it's the cloud controller. What will happen then is Kube API server will talk to the Cloud Controller Manager, and Cloud Controller Manager will talk to the cloud, to the underlying infrastructure provider, to provision that load balancer, because likely that load balancer is going to be a cloud resource and not the resource that's running in the Kubernetes cluster. The last thing here in the control plane is kube scheduler. That's the component that basically defines when we create pods and other workloads. That's the component that defines on which nodes those pods will be scheduled. So if I say I want 5 instances of Nginx, is the kube scheduler that ultimately will say this instance runs on this node, this instance runs on this node, et cetera, et cetera. Now on the worker node side, there's 2 very important things installed on every worker node. One is called kubelet, and kubelet is the main service on the node. It's responsible for checking the desired state through the kube API server and starting and stopping pods on the local node. It basically manages the local node and makes sure that whatever desired state is defined in the etcd database, then the information that it gets through kube API server, the local state will match that desired state. So it starts pods, stops pods when needed. It monitors the health of the pods and updates pod status, and also monitors the health of the node and updates the node status. So this is, kubelet is the reporting mechanism, for example, how you basically, the cluster knows how much memory, how much CPU cycles that node has available, so the scheduler can now make decisions where to place the workloads. The second important part there is kube proxy. And kube proxy, it's not actually a proxy, it's called a proxy, but it's a component that essentially manages IP tables routing rules. And it defines the local kind of part of the network traffic routing that the things like services and ingress, etc., are responsible for. So that's how the networking magic happens within the cluster. And the last thing I'll mention that's not on this diagram, but it's an important component of the whole thing because it's how you interact with the cluster, is kubectl. Kubectl is a command line tool, and this is the core tool that you'll use to do anything with the cluster. It supports both imperative and declarative use. That essentially means that you can run kubectl and tell it to start a new pod, or you can create a YAML or JSON configuration file to describe the desired state and tell kubectl, hey, apply this configuration and then it will upload that configuration, submit that configuration to the Kube API server, and then the magic in the background will start happening. All kubectl does actually doesn't do any processing at all. All it does is it knows how to talk to API server, and it knows how to pass all the information that are part of those switches and commands and files that you can feed it, etc. It knows how to pass all of that information to the API server. It does do syntax validation, so it does some rudimentary, at least, checking of the YAML files, etc., so that you don't kind of overload the API server with some garbage data. Okay, gonna pause for a bit, see if there's any questions. I don't see any. All right. So the next thing I wanted to cover is now kind of knowing roughly what Kubernetes is and what components are running in the Kubernetes cluster, or what the architecture is. What I wanted to next to walk through is how, like, what happens within the cluster when I, for example, create a new deployment. So let's try that, and it's kind of a step-by-step thing that I call a life story of a deployment. So the first step usually is, let's say I'm a cluster administrator and I create a new deployment. As I mentioned, that can happen in two ways. I can either say kubectl create deployment and provide all the configuration there, so kind of the imperative way, saying deploy this thing, or I can do it in a declarative way. I can create a YAML file that describes the deployment and basically tell kubectl to apply that configuration to the cluster. Either way, what happens in the background is kubectl talks to the API server and tells basically API server, I want to create this new deployment with this image, this many replicas, etc., and all the other parameters that are needed to create that deployment. So all kubectl does is makes that API call and sends the information to the cluster. The API server, when that call happens, it will save that state, save that deployment object into the etcd database. At this stage, the API call ends, kubectl returns back to your command line, and there's a new object that's present in the etcd database that describes the deployment, but no workloads, nothing is running in the cluster yet. So nothing's happened apart from updating the etcd database. So in the etcd database now we have this deployment object, and the deployment object has a new desired state, meaning that it has a description of what pods are part of that deployment, what images those pods should run, how many replicas should the cluster run, etc., etc. So number of replicas, images to use, any workload configurations defined like config maps, secrets, etc., etc., or manually injected through some environment variables or command line arguments, etc. And also things like volume mounts, so like mounting, storage, etc. So we have this deployment object in the database. And now this is where that controller manager comes into play. So controller manager now, as part of the controller manager, there's this thing called deployment controller that's responsible for deployment objects within etcd. So it comes along and sees this new deployment object, but sees there's no replica set that's associated with that deployment. And I haven't talked about replica set, but it's kind of a deployment object is a hierarchical thing. So deployment object itself is responsible for things like rollouts and kind of the strategy for the rollouts, but replica set is strictly responsible for just maintaining a set number of pods that corresponds to what deployment wants. So the deployment controller sees there's a deployment object, but there's no corresponding replica set object, and creates the replica set object. And then the replica set controller, which is also part of the controller manager, comes along and sees, oh, there's replica set object, but there's no pod objects in the etcd. So it will create the required number of pod objects. In this case, the deployment said, I want 3 replicas of that pod. So the replica set controller will create 3 pods that correspond to that template. Again, all of this still at this stage happens in etcd database. No workloads are running still. The next thing that happens is scheduler comes along. So scheduler defines where the pods are going to be scheduled to which nodes, and it sees a bunch of pods that haven't been scheduled yet, that haven't been assigned to a specific node. So it will look at the status of the current status of all of the nodes that are part of the cluster, where the RAM is available, where CPU is available, and also deployments can specify some restrictions onto which nodes that deployment is allowed to be scheduled. So there's some constraints that you can create. So scheduler takes all of that into account and basically says, okay, this pod I'm scheduling to this node, and this pod I'm scheduling to this node, etc. So all of that, again, is purely within etcd database. The application, the containers are not started yet. So that magic happens on the worker node. So on the worker node now, we have this kubelet that from time to time is checking if there's any new pods that are scheduled to that node that haven't been started yet. So it finds now that pod object within the etcd database, sees that that pod object does not actually have any corresponding containers running on the node, and now the kubelet will start those containers and inject all the configuration, etc., and pull images and do things like that. So this is basically the actual magic, where actual magic is happening, is the kubelet checking the state in the etcd database and making sure that whatever's running on that node matches to the desired state. Once all of that is done, kubelet will also update the status of the pods. So basically, when you do like kubectl get pods, for example, those pods will have a status, whether they're starting or there's like crash loop or it's running. That status comes from the kubelet that checks what containers are running on that node where the pod is scheduled. Okay, so that's the second big part, and I know I went fairly quick, but I think kind of understanding, at least at a very high level, those building blocks will help us understand the threat model that I'm going to talk next, and basically all the other things that I'm going to talk about. If there's questions, I'm going to pause for just a sec to check if there's any questions.
I was just curious about, you mentioned the using kubectl with the YAML file for your deployment. That is not the Helm chart that I'm thinking of,
right?
Nor the Helm chart that I'm looking for. But the I'm wondering, in terms of using automation in scanning files for bad security configurations and just bad practices. Are there things there that we can use?
So there are basically tools to do linting or just static scanning of Kubernetes deployment YAML files. There's open source versions, and there's also commercial tools that include that functionality. I'll mention some of the open source tools in one of the later slides, but definitely there's scanning tools that help with that to kind of highlight potentially dangerous configurations and just generally, so like typical static code analysis, but that knows the context around the Kubernetes YAML file specifically.
So I'm a big fan of the smokeless ashtray and the oven that cleans itself while I sleep. So any form of automation to be able to tap me on the shoulder and say, "Wake up! Don't do this," is really useful.
Yeah. So the tools that I've seen in terms of the workloads, the tools that I've seen, they generally work as kind of as part of the CI/CD. So you feed it those YAML files, and they'll give you scanned results, so like a typical static code analysis tools. I haven't, maybe I didn't come across, but I haven't seen, or maybe I'm wrong. There's tools to scan the runtime as well. So there's a difference. Like, here's YAML files that I have in my source code repository, and I want to deploy them. but before deploying, I can scan them to see if there's any issues. So that's one category of tools. There's also tools that scan your cluster in terms of cluster misconfigurations and possibly dangerous configurations of the things that are running in the cluster already. Those might or might not have corresponding YAML files, so they work somewhat differently. They talk basically to the API server and give you opinions about the running things. But yeah, there's I'm going to mention some tools, and there's definitely a lot of the commercial products that do exactly that. By the way, again, we're kind of getting ahead of ourselves, but there's CIS benchmarks that is for Kubernetes specifically that talks about things like that. So there's also tools that specifically run tests against the CIS benchmark and find misconfigurations in the clusters as well.
Awesome, thank you.
All right. Okay. Now, to continue, why am I talking about managed Kubernetes? So to me, just going through those handful of slides and seeing what like the architecture of Kubernetes and how it works, it's a very complicated ecosystem. It has very much Lego-like architecture, meaning that those different components are essentially related but separate projects, and they can be deployed in a variety of different ways. And so there's so much complexity in the ecosystem that standing up and maintaining and managing an on-prem or kind of your own Kubernetes cluster is not a trivial task. And especially if you're just starting out, the best advice that anybody can give you is go with a managed Kubernetes. Let AWS or Azure or Google or whoever else manage that cluster, manage the control plane for you, so you can focus on your workloads and focus on what you know better and where you can add more value rather than trying to secure the control plane and the kind of the core Kubernetes components themselves. So there's multiple ways to deploy and configure those clusters. That also means there's multiple ways to screw it up. And there's also a number of things that happen outside of the clusters with like networking and the CNI plugins, any sort of auto scaling if you want to basically be adding nodes to the cluster automatically as your workloads grow, and load balancing and public and private IP mapping and things like that. So it's not a trivial task. So if you ask me, I think the best thing to do is go with the managed deployment and basically use Kubernetes as a platform and let a cloud provider that has expertise in Kubernetes to run a lot of things for you, which also means that they'll secure a lot of things for you. The parts that they're responsible for, they're going to be responsible for securing. Now let's talk at a kind of high level about the Kubernetes threat model. So again, going back to the architecture, at a very high level, the places where things can go wrong are essentially the etcd database, if it happens to be exposed outside of the control plane, the kube API server. So think about anybody who can interact with the API server, especially if they have credentials, can potentially do things in the cluster, and the worker nodes themselves. And the worker nodes, the big part of that, and this is the piece that we're going to focus the most, is let's say I'm running a workload in the cluster. That workload, my application basically becomes compromised. What else is now exposed because of that that's also running in the cluster as well? So kind of, in my mind, there's 4 main scenarios that we should be concerned about that definitely are part of the Kubernetes threat model. So that's attacks on the control plane. So is the control plane exposed? Are the credentials exposed? That kind of thing. Then compromised applications running in the cluster. I have a workload running in the cluster. Somebody hacked into that workload. Now what? Compromised user accounts and credentials. This is basically securely managing access to the cluster. You're likely to have some users that can interact with the cluster. You're likely to have some CI/CD pipelines that can interact with the cluster. So securing those credentials and access to the cluster itself, and managing basically credentials in a secure way. And the last part is kind of similar to the second bullet point, but compromised images. So if I'm running some workload in the cluster, that workload can be hacked into, but you can also have a supply chain type issue if that image that you're running comes from some outside entity. It's public image, and the image itself is compromised. Now you have something that attacker controls running within your cluster. As a side note, this is quite an interesting read. In 2018, CNCF, this is the foundation that maintains and manages Kubernetes project. They've done an RFP, and they've done a huge security audit on the Kubernetes ecosystem. And by ecosystem, I don't mean like third-party components. I mean the things that basically comprise the core Kubernetes code base. And so they've completed that audit in 2019. And so if you the audit report is publicly is published on the GitHub. It's public, and it's actually quite an interesting read. I'm going to share all the links afterwards. You don't need to write them down. I'm sure we can post them either in YouTube as comments or somewhere else. So for the next part, I'm going to focus on this compromised application running in the cluster. As I said, the image part is fairly similar, and I think the kind of the control plane and securely managing credentials are a slightly more straightforward scenario. But if you're running something in the cluster that's externally exposed, chances are at some point of time it can be compromised, and it's really important to understand what is the exposure, what's happening, what's the actual risk to the cluster itself and to the other things that are running in the cluster when that happens. And so if we talk about that scenario, essentially there's three big parts that we need to be aware of, or we need to focus on. The first one is network access and lateral movement. The second part is Kubernetes cluster credentials. And we've talked about credentials as a separate kind of threat or a separate risk, but this is specifically about the credentials that are exposed within the cluster that are available to that workload. And the last part is container escape. So if you are not securing your workloads or running them appropriately in the cluster, there's a high possibility that an attacker, a successful attacker, can escalate their access from that container and basically get access to the host. And as we'll see in just a bit, that's a really bad thing. Okay, pause for another second to see if there's questions. Yeah, Pocket Java, you're right. DigitalOcean also has an affordable managed cluster. I think with DigitalOcean, you just pay for the compute. So like if you're running a cluster of 3 or 4 nodes, you're just paying for those nodes and you get the control plane essentially for free. And once we get into the demo, just FYI, the demo that I'm running the cluster in DigitalOcean. It's quite an easy way to spin up a new cluster. All right, so let's talk about networking for a bit. Networking is not surprisingly, or maybe not surprisingly, networking is not a core part of Kubernetes. Basically, Kubernetes says, hey, here's the API for any pluggable networking module that can be used as part of the cluster, and you can use whatever module you want. And there's actually a number of networking plugins. They're called CNIs, Container Networking Interface, that you can use. What's important here is a couple of things. Firstly, at the core of Kubernetes is an open networking model, which means that by default, any workload that you deploy into the cluster will be able to talk over the network to any other workload that's deployed into the same cluster. That's essentially the #1 goal of CNI, is provide that overlay networking so that different workloads can talk to each other. Because if you think about it, there's very likely that there's going to be a lot of dependencies like microservices or databases, or like web UI versus application server versus a database. So it's very likely that those components, those workloads that are running in the cluster, will need to legitimately talk to each other. But essentially, by default, there's no segmentation, there's no traffic filtering between the components. Now, Kubernetes has this notion of network policies. This is a native way to define, to restrict traffic between the workloads within the cluster. But the caveat here is that those network policies have to be supported by the CNI, and not all of the CNI support the network policies. And this is just a quote to give you an idea. This is just a quote from Kubernetes documentation. Kubernetes imposes the following fundamental requirements on any networking implementation. Pods on a node can communicate with all pods on all nodes without NAT agents. It basically means that overlay networking, its intended use is to provide that overall connectivity. Now, what are the risks of all of that? Firstly, as we're talking about the managed Kubernetes clusters, we need to think about the instance metadata endpoints and access to those instance metadata endpoints. Those can expose some temporary credentials within your infrastructure provider. Then there's the kind of bootstrapping credentials that are part of how the cluster is built by the infrastructure provider or by the managed Kubernetes provider. So there's some bootstrapping credentials that might or might not be important, and those are generally also available through the metadata endpoints. And this risk, just to be honest, this is not just a risk of like compromised workloads. This can be exploited potentially if there's some sort of SSRF type vulnerability within one of your workloads. The second part is control plane and node access. By default, Kubernetes API is exposed within the cluster. So essentially, any workload can connect to the cluster and interact with the cluster. Sometimes this is useful, but not always. And we're going to talk a little bit later about the credentials for those workloads. But essentially, again, by default, the Kubernetes API or the control plane is exposed within the cluster. Now, the second part, I'm going to talk on the next slide about the Helm and the issue with and what it is and the issue with version 2. The last piece is essentially a network-based lateral movement. So if you've got any sort of complicated microservices or like databases and etc., again, by default, your workload will have access to all of that, and that creates a potential for lateral movement. Now let's talk about Helm and specifically Helm version 2. Essentially, Helm is a sort of like a package manager for Kubernetes. So the applications that you deploy in your cluster might not just be the code that your company or you wrote. You might also be using sort of third-party prepackaged applications that are useful for, let's say, log collection and metrics collection and monitoring in general and that kind of thing. And so Helm is a very popular package manager that allows you to use basically almost a single command to deploy a whole infrastructure, like the kind of the log collectors and the UI and the database and all of that sort of packaged in one way that's easy to deploy. It's quite popular, and there's at least until recently, there's been 2 major versions that are still available today. Version 1 and version 3. And those versions, and this is why I'm focusing on this, those versions work very differently. So the way version 1 used to work is, so they have these, the packages that Helm manages and can deploy are called charts. So there's this repository of those charts that Helm can connect to and kind of pull those charts from. And then Helm, the CLI component, doesn't do the work at all, but it talks to this sort of this like Helm's API component that actually does the work. So this is sort of like a Kube API server, but for Helm, they call it Tiller. So that's the service that's running within the cluster, and the CLI just connects to the service and basically says, hey, I want this chart to be deployed, and then Tiller actually talks to the Kube API server and provisions all the resources and deploys all the resources. Which also means that Tiller has privileged access within the cluster. You can limit that access by namespace, but even within that, the permissions of the Tiller are quite extensive, and definitely it's able to deploy new things and delete deployments and do things like that. So This creates an issue with kind of potential issue with the lateral movement, because at least by default, that tiller, that API, this gRPC-based API of the tiller is not authenticated, which means that unless you implement network policies, any workload within the cluster potentially can talk to the tiller and take over the cluster completely. So if you do use Helm, especially if you do use Helm version 2, be careful, make sure that you know what's happening with the tiller, or alternatively, ASAP migrate to version 3 that doesn't have tiller completely, and so that Helm CLI component just uses your credential to talk to the Kube API server directly. And this is again from the Helm documentation. Default installation applies no security configurations, which is always great to see as a security professional. Any questions so far?
We're just, I think they've reorganized their
Oh, okay.
slide. So I'm just about to post an updated link. Instead of it being a working group, they have a SIG-security. Where
okay, cool. That's good to know.
They have a sub-project which is called the SIG Security External Audit Sub-Project.
Yep.
And so I'll post the link for that, which I believe
Perfect.
has updated audit documents.
Thank you. Any other questions? I don't see anything. Okay. Then let's talk about cluster credentials. Out of the box, Kubernetes supports multiple authentication options. It does internally uses certificates and tokens, and so it includes sort of a mini CA component that kind of manages credentials and certificates and keys for nodes and things like that. But it can also support things like OpenID Connect. The important thing to understand is that Kubernetes itself has no concept of a user. So it has a concept of a service account, which is ability to assign permissions within the cluster to workloads, to like your application. So if your application needs to interact with a cluster, then you can assign permissions, and those permissions will be kind of automatically mapped into the workload, and the workload will be able to use them. So those are called service accounts. But Kubernetes itself doesn't have a concept of a user, like a person who will interact with the cluster. So that is essentially external to the Kubernetes. And in probably 99% of all the cases, you will be using some sort of OpenID Connect based integration. And in majority of the cases, your managed Kubernetes provider will have capabilities to use the authentication that the service provider uses for its own users, like for example in AWS, the IAM accounts to give you access to the Kubernetes cluster as well. So that OpenID Connect will take care of that single sign-on. So the way that role assignment to the workloads happens is, firstly, all Kubernetes pods have a service account associated with them. Even if that service account doesn't have any permissions, even if you didn't define that service account, it will be assigned a default service account. Again, by default, there's a token that basically contains the credentials of that service accounts that is mounted within the pod. So unless you've turned this off, and we'll see how that's done in just a bit, but unless you've turned this off, any workloads running in the cluster will have access to this token that can be used to somehow interact with the cluster. In a lot of cases, that has limited read-only permissions, but again, you will be able to use the token and to connect to the API server and do some things with it. Now, at the core of the Kubernetes permissioning is the RBAC model. So there's kind of 4 objects that are defined within Kubernetes, and those are role and role binding, and cluster role and cluster role binding. So role is a set of permissions, a definition of a set of permissions. So you can say This role grants read access to all the pods, or grants read access to pods in this namespace, or grants read access to pods to only the pods that have a specific label. So it's quite flexible, but ultimately role is defined in terms of what objects within the Kubernetes control plane this role gives access to, and what kind of access. And that what kind of access generally is get, which is read, list, which is also read, but basically list all the objects, and edit, or basically write access. So, and role binding associates a specific role with a specific service count. So to provide some permissions to some workload, there's a service count that the workload that is mapped to the workload. Then you create a role that defines the permissions that you want to give that service count, and then you create a role binding that basically says, okay, this service count gets this role, and this is how the permissions are mapped to the service count. Cluster role and cluster role binding work absolutely the same way. The only difference is role and role binding are namespace resources, meaning that the permissions that are provided are for specific namespace where that binding is created. And cluster role binding is a cluster-wide resource, or a cluster-wide object, so that basically the permissions that are defined in the cluster role will be applicable to any namespace within the same cluster. But apart from that, kind of the scope, namespace or cluster-based, there's basically no difference between those things. Okay, any questions on this? Oh, there's a new link. Thanks, Garth. Okay, so we've talked about those three things, right? So there was the networking and lateral movement, there was credentials that we just covered, and there's containerscapes. For containerscapes, I'm not going to do a deep dive. I'll just highlight a couple things overall, but there's a really, really great talk published on YouTube by Brandon Edwards and Nick Freeman. It's called Compendium of Containerscapes. And if I can, can I copy link address? Let's see if I can post. Maybe not. I can't post in comments, but I can post in people. But anyways, so we'll post the link, but or you can just Google Compendium of Containerscapes. That's really detailed, really good talk on not just Kubernetes, but containerscapes in general. But so containerscapes, what this essentially means is when containers don't contain. So it's basically the scenario is, if I get access to some container, can I now escalate that access to get access to the host that's running that container? So basically escape that that isolation that the container should provide. So how this happens is multiple ways, but the most common ones, there could be a vulnerability in the container runtime, and this can be like containerd as an example. That's the runtime that's used by Kubernetes. But if the runtime itself contains a vulnerability, some of those vulnerabilities allow container escapes. The second option could be an outdated kernel. So if you have a kernel level vulnerability that allows you to basically do privilege escalation, that potentially can allow you to escape the container and kind of land on the host. And then there's security misconfigurations. This is there's a number of important things that we shouldn't do. Firstly, and this is very kind of not very common, but fairly critical. First thing is mapping a Docker socket into the container, or basically in general, allowing access to container runtime API within the container. Then there could be some sensitive paths mounted from the host. So those sensitive paths include things like /etc/prog, basically the things that give you access to things on the host that potentially you can use to escape the container. And then excessive capabilities, and these talk about like things like netadmin and sysadmin, basically giving root access potentially to the host. The next thing is privileged containers. So privileged containers essentially means that those controls that make containers are not applied to privileged containers. So privileged containers can do things like mount file systems. They can do things like install kernel modules and things like that generally containers shouldn't be able to do. And you are able to start and run privileged containers within Kubernetes as within Docker, plain Docker as well. And that's a dangerous thing. And occasionally, though, some of the system components, especially the security tooling that we'll talk about in a bit, they need those privileged kind of privileges because they interact with the host and they want to see all of the pods and containers that are running on the host and on the node and do things like that. And then the last thing is container UID. This is not a kind of direct container escape risk, but essentially if you're running a workload, a process in the container as user ID 0 or root, that creates a much higher chance of somebody basically being able to escape that container. All right, I've talked a lot. And I hope we'll be able to do a quick demo unless there's questions before we dive into that. So if there's questions, please post. If not, I'm gonna see if I can get the demo going. All right, I don't see any questions. So for the demo, I have this specifically constructed environment that runs a Kubernetes cluster. And basically, I wanted to illustrate a couple of things. So I wanted to illustrate that network-based lateral movement, how that happens and what it looks like. I wanted to demonstrate things around credentials and how they're exposed in the pods. And I also wanted to demonstrate with regard to container escapes, how those container escapes can happen potentially, or at least some of the vectors. And the scenario that this demo kind of represents is exactly the kind of the most common threat vector or attack vector that we've been talking about. It's basically I gained access to a workload that's running in a Kubernetes cluster. Where can I get from there? So this basically is a web shell that's running as a workload in the cluster that I provisioned. And the first thing I'll do is let's try to explore the environment and see where we are. So we can list the processes, and this right away tells me with a very good probability that we're in a container. There's only 3 processes running, and the process ID 1 is not in it, but in fact is a node that's running some application. I can also check environment variables, and by seeing that there's environment variables like this Kubernetes port, I have a kind of there's a good chance that we're running in a Kubernetes cluster. What this Kubernetes port environment variable is, it's a variable that's automatically injected into the workloads that basically tell the workloads where to find the Kubernetes API server if they need to talk to one. So this is where Kube API server of this cluster is accessible within the cluster to any of the workloads. Now, first thing we talked about, if you remember, with regard to the network lateral movement, maybe I should clear the screen. Okay, is access to the instance metadata. So I want to try to do that. So we're connecting to the metadata IP, and I'm requesting this user data information. There's some interesting things here. We're not going to kind of dive deep and try to use them, but remember when I was talking about the bootstrapping credentials that are part of the cluster provisioning. So as an example, this Kate's CA cert defined here as a variable that's one of those kind of bootstrapping credentials. That's a root certificate that should be trusted across the cluster. And there's somewhere here, bootstrap token. This is the token that basically allows the newly provisioned node to join into the cluster. Now, for next steps, we want to explore the cluster a little bit further, and for that, it's going to be much more useful if we had a kubectl available. So, what I'm going to do is I'm just going to download kubectl, make it executable, and then we'll be able to interact with the cluster because we're on a workload that's running in the clusters. First thing I'll do is kubectl get service, and I'll add -a. This is just to show you what services are defined in the cluster. And -A essentially tells a kubectl to list services in all of the namespaces. So you see that there's default namespace here, there's ingress nginx namespace, there's kubesystem. So if you remember, kubesystem is where all the Kubernetes control plane processes run. There's also Kubernetes dashboard, which looks quite interesting. So to explore further, this is the piece that I want to take a look. I'm going to try to request that Kubernetes dashboard. And so the way the workloads within the cluster interact with each other is there's a internal DNS service that's part of the Kubernetes cluster. And when a new deployment or a new pod or a new service is deployed, those things are registered in that internal DNS service. So the workloads within the cluster can use that service to reference each other using names and don't need to know each other's IP addresses. And so what I'm doing here is I'm connecting to Kubernetes dashboard.kubernetes-dashboard. This doesn't look fancy, but what this in practice, what this is this part of the name is the namespace, and this part of the name is the name of the service. So if I have some service that's running in the cluster, I can connect to it from within the cluster by using the service name dot namespace name. And we see that it responds, so we have access to it, and and this is Kubernetes dashboard, which is a graphical user interface for managing Kubernetes. So what we'll try to do next is we're trying to grab a token for the service account that's assigned to this workload. So remember how I was talking about that every workload has associated service account, even if you don't define one. And by default, the token, the credentials for the service account are mapped into the pod. And the place where they're mapped is under /var/run. And specifically, all the files that we need are actually in this path under kubernetes.io/service account. And so we see there's a token, there's namespace, and there's certificate. And we're going to grab the token because we're going to use the token, try to use the token when we connect to the dashboard. So first thing I've done is I've grabbed the token. So I now have it. The second thing I'll do is, so this Kubernetes dashboard, it runs within the cluster, and I want to connect to it using my browser. So all I'll do is I'll start a tunnel that will allow me to connect to that internal only service from my browser. So I'm going to use something called local tunnel, but this is essentially a node module that can do things like similar to ngrok, if you ever used ngrok to expose internal services onto the internet. So we're going to install local tunnel, and then I'm going to need the token, and then I'm going to create this new tunnel. And so what I've done is I've basically said, hey, this is where I want to tunnel traffic to. It gave me this unique URL that I can now use to connect to. And then I'm going to grab this token. This will be my credentials. So what I'm seeing here is that service that's running within the cluster. So I can, using my browser, I can talk to it using that public tunnel. And I'm pasting the token that I've grabbed, and I'm sending it, and we can explore this cluster. And I'm gonna pause for a sec to see if there's any questions. Would you allow privileged init containers to start your pod deployment? That's a good question, Kevin. Potentially, I think I tend to be fairly practical about privileged containers, and my kind of rule of thumb is as long as that workload is not exposed to the outside world, it's generally okay, especially, and even better if it's not exposed within the cluster. So the privileged workloads that basically do something within the cluster, do some maintenance that don't expose network services, are, in my view, are generally okay. But init containers might be fine as well, because they're kind of prepping the environment for the actual container that runs the workload. But it also probably depends on the details. And like, frankly speaking, there should be some sanity check, basically saying, does this container actually need to be privileged, or is there a way to run the same thing without giving it a privileged setting? I'm not sure if I answered your question. There's another one. Is there any kubeconfig file in this workload? There's no kubeconfig file in this workload, so the token is basically the credentials that would normally be part of kubeconfig, and the Kubernetes _port, the environment variable, basically points to the right API server. So all the bits and pieces are there, and I think you can create that kubeconfig file if you need to, but there's no sort of kubeconfig file that's dropped onto the workload. But we'll see on the node, and when we get to the node, we'll see there's kubeconfig files there that the kubelet is using. Okay, I don't see any other questions. Yes, Kubernetes dashboard, the Department of Redundancy department. Yeah, it's not really redundancy. Like, it was redundant in this case, but it's service.namespace, and they don't necessarily, they're not necessarily going to be the same. So it just happens to be the same in this case.
I couldn't resist. Sorry.
Yeah, of course. Okay, so this is what's running in our cluster. So we see this web shell, we see the pods that are part of the web shell. So web shell is the deployment. This is the actual pod that the deployment started. And we can see other things. It's actually, there is a config map. There's persistent volumes are basically a way to mount storage into the pods. There's some secrets and storage classes and things like that. So the service account has relatively limited access within the cluster, so it doesn't see everything. So for example, if I even see namespaces, so if I click on namespaces, I can even see there's nothing to display here, no resources found. But we've seen that there are namespaces in this cluster. There was default kube system, Kubernetes dashboard, and things like that. It's just that this service account doesn't have a lot of permissions. But the permissions that it does have is it is able to edit itself. It is able to edit the deployment that defines this web shell. So that's what we're going to do. And to give you a context or an idea, what I'm trying to do is, now that I have access to, so we've landed in a workspace. Through the network, we did lateral movement and got access to this dashboard. Now we're going to use the dashboard to escalate that workload that we're in and get access to the node that's running the workload. And to do that, remember when we talked about the privileged containers, this is basically exactly what we're going to do. So so what I did, I opened that this is the web shell deployment. This is the deployment that's running the web shell. I went into it and I clicked this edit, and this is the YAML that describes the deployment. So this is basically everything that the cluster knows about the deployment. And I can actually change this YAML right here and then apply. And it will update the deployment and redeploy the running pods. And what I'm gonna do once I check my cheat sheet, what I'm gonna do is, so this part under spec, this defines the containers the template for the pod and the containers for that pod. And so within the containers, I can do security context and then do privileged true. And then another thing I'll add is host PID and true. These appear in different things. So security context is defined for container, but the host PID equals to true, which basically removes namespacing of process IDs, is defined for the whole pod. And this is why these are at different levels. And I'm going to click update and hope for the best and see if I can restart this. Okay, so now I can close this dashboard. So now we're in a new container because that once I've updated the deployment, it killed the old container, old pod, and it provisioned a new pod. And now this pod has all of those things that I configured enabled. So first thing we can see is when we do process list here, we see all the processes on the host. And this is what that host PID true did. And we also have the privileged flag. So a lot of the constraints that are present for containers are not present in this container. So for the next step, we'll need kubectl again, I think. Yeah. So I'm just doing the same thing. So I'm downloading kubectl and then making it executable. And now the thing that I'll do, and this to demonstrate, if I can type, this to demonstrate why that escalation to the node can be important. In this cluster, I have a secret that's called super secret, and it's defined in namespace named secret holder. So what I'm trying to do now is from within that workload that I'm in, trying to get that secret. And so I'm saying get secret, this is the name of the secret, and this is the name of the namespace. And that workload does not have access to the secret. So the service account that is mapped to the workload does not have access to the secret. But don't worry, we will gain access to that secret in just a minute once we land onto the host. Now, I'm not gonna do much of an explanation for the next command, but this is a way to basically escape the container if you have a host PID and you have the containers running in privileged mode. It basically says the containers are actually like, there's no single concept that in the Linux kernel that constitutes a container. It's a number of different things working together to provide that sort of isolation. And those things are different namespaces, like a network namespace, user ID namespace, process namespace, and things like that. And also the C groups that can enforce limits on the CPU and memory use and things like that for specific processes. So what NSEnter does is it basically switches the namespace. And what I'm doing is I want to switch to namespace of a process with process ID 1. And because I see the process on the host, we're basically getting full access to the host by using this command. And so here we're saying mount means that I want to switch mount namespace to the target process. I can't remember all the flags, but the main ones are the network, the PID, and the mount. So, and the last argument bash is basically the command to run in that switched namespace. So once we do that, and see the host name also switched here. Once we do that, this shell is now running on the node. And because we were running as root user in that container, once we jumped onto the node itself, we're still a root user. So if I do ID, you see that I'm root. So this access now is, this shell now is running on the node. So now back to that kubeconfig thing. If I list files under /c Kubernetes, this is the configuration files for the kubelet. And by the way, kubelet, as we saw, kubelet talks to the API server a lot because it needs to check what pods are defined in the clusters so that it knows when it needs to provision new containers or when it needs to kill the existing containers that are no longer needed. And the credentials that kubelet uses to talk to the kube API server, they're stored in this kubeconfig file. So that's the kubeconfig. It's in kind of this special location, but this is the kubeconfig that the kubelet will use when it's talking to the cluster control plane. What I'm going to do is I'm going to use that kubeconfig. So I'm doing kubectl, and I'm not doing / because kubectl is available on the node by default. And I'm saying, okay, use this kubeconfig that I found, and then run get secret, and it's basically the same secret that we were trying to get, but we're not successful. And now I've gained access to the secret. And remember when I talked about the difference between secrets and config maps? So this is what it looks like. So this is kind of the core of the secret, the data of the secret. So I've got one item there in that secret called message. And this is the actual secret, but it's base64 encoded when it's displayed onto the screen. So you never essentially see the plain text secret. This is the main difference between config maps and secrets, or at least kind of usability wise. But not to worry, we can base64 decode whatever. So I'm essentially running the same command, but I'm gonna base64 like use JQ to extract just the message and then base64 decode. And so now we get access to the secret. Another thing I'll show you, so we have, if I list IP addresses on this node, as you can imagine, there's a whole bunch of them. There's kind of, the node has its own IP address, there's a public address, there's a private address, but also there's a bunch of virtual interfaces like the Cilium host and Cilium net. Cilium is the CNI that DigitalOcean uses, at least by default. And so you see that there's a lot of networking that have been provisioned for the cluster to run. And then we can also see, if I can spell it correctly, we can see all the containers that are running on the node. This is just for kind of for fun to see. Okay, I'll do copy paste. I cannot type today. So I'm using CTR, not Docker, because Kubernetes switched from Docker to like plain containerd not that long ago. And the version that I'm running here on DigitalOcean is a newer version. So there's actually no Docker installed, I think, on this host. Yeah. Oh, there is Docker. Okay. But it's not running containers in Docker. So Docker knows nothing about those containers. But if I interface straight with containerd, I can list the containers. So these are all the containers that run the workloads and the system components of the cluster itself. Okay, I'm gonna exit from here back to my workload, back to my container. So now we're in the container. The last thing I want to show you is the list of IP addresses within the container. So when we updated the deployment, I said use the host process ID namespace, but the network ID namespace was still kind of native for containers. And so all of those IP addresses that we have on the node, they're not exposed in the container in the workload. Okay. So that was the tech part. I'm going to check questions and I'm going to talk a little bit about how to fix a lot of this. Okay, I think everything you can do in the dashboard, you could also do from the container where you ran kubectl. Yep, absolutely. I was just showing more for kind of demonstration of network pivoting, and also just to show the fact that if something's running as a cluster-only service, doesn't necessarily mean that things outside of the cluster cannot access it. But yeah, absolutely, you can use kubectl and do exactly the same thing. It's just more visual the way we did it through Kubernetes dashboard. Is there a tool to scan a pod or a YAML file defining a pod for common container escape vulnerabilities? Yeah, so those YAML static code analysis and linting tools, I'm going to mention them in a slide in just a bit. They can scan for common misconfigurations, and those include like privileged containers and things like that. All right. Okay, so how about fixing at least some of this now? I think we should still have kubectl. Okay. So first thing we'll do is we'll implement a network policy. Again, this wouldn't make a lot of difference in this case, but as a general, to kind of give you a general sense, it's a good idea to use network policies to segregate the workloads within your cluster that don't need to talk to each other. And so this is more like a demo and not necessarily this is a required step. So first thing we'll do, we'll check again that we have access to that dashboard, and we do. And now we're going to create a network policy, and I'm going to use this quite a nice visual tool for network policy creation from Cilium. It's called a network policy editor. It's basically a visual way of creating network policies. So I want to create a new network policy that will limit access to the Kubernetes dashboard to only things that are within that same namespace. There's a kind of tutorial how to use it right here. My policy is going to be fairly simple, so I'll give it a name, Kate's dashboard policy. I'll give it a namespace so that Kubernetes dashboard was running Kubernetes dashboard namespace. And then pod selector is basically what pods will this policy apply to. And maybe I should be using copy paste so I don't mistype things. And so that Kubernetes dashboard pod has a label named Kates-app with a value of Kubernetes dashboard. So this defines name of the policy and what this policy applies to, right? And now there's kind of two sides on this editor. There's the ingress. This is what can connect to this pod or to these pods, and the egress, what these pods can connect to. So for now, let's just forget about egress and focus on the ingress. And what we'll do is there's kind of three different things. There's outside cluster. So what outside things can access the service within the same namespace and within the cluster. What I'll do is I'll highlight this in the namespace and say allow any pod. And as soon as I've done that, these two arrows turned red. And the reason for that is when I didn't have any network policies defined, all the traffic was allowed. But as soon as I define a network policy and say, okay, ingress is allowed from all the pods. This is essentially what this part of the YAML means. That will automatically block all the other traffic. So these arrows are turning red. So now we've defined this network policy. I'm going to copy and paste it, and we're going to apply it. Looks pretty good. And then apply. Seems to be working. And now we'll do that curl again. Now this access no longer works because we've limited access to the dashboard. But if I do like curl, this access still works. So we didn't restrict egress from the workspace. We just restricted ingress into the Kubernetes dashboard. And this is how the network policies work. Okay. The second part that I'll do is I'll show you how to remove that mounting of the service account token within the workload. So those tokens are mounted under run secrets or var/run/secrets. It's basically symlinks pointing to the same place. So I can show you that at the moment the service account token is mounted. And what we're going to do, and this also demonstrates another way of editing the configuration or editing the deployment. So we've used that Kubernetes dashboard previously, but you can also do it through command line. Maybe I'll switch the editor first. I'll do kubectl edit deploy web shell. This is basically the same thing we're doing through Kubernetes dashboard, but in a command line. And what I'm going to do here is a couple things. Firstly, we're going to remove this security context and the host PID. And then we're going to add, see that there's this service account definition. So web shell-sa is the service account that's mapped to this pod. And what we're going to do is we're going to add auto mount service account token and set it to false. And I think that's it. There's another security context here. That's fine. We're going to save and see terminal disconnected, which means that the deployment is now updating and provisioning new pod and removing the old pod. So now, firstly, we're back into the normal contained container mode, but also when we check the /run to see if the token is mounted, we no longer see those tokens. What this also means is, so if I download the kubectl again, what this also means is this workload no longer can talk to the Kubernetes control plane. Remember in the very beginning when we did kubectl get services from all namespaces, we were able to get that information. Now we can try to do get deployment or get service, and it no longer works because we don't have the token mounted. And that is the end of the demo. Let's see if there's any questions. Okay, is NSEnter typically available? I've never heard of it. NSEnter is often available. So for example, if you run Alpine image, it's available by default. You don't need to install it. But also, unless you're using distroless images for your workloads, often you will have operating system package manager available. So even if it's not available, if the egress and network traffic is not blocked, you can typically install it. But it's not unusual for NSEnter to be available. It's basically a standard Linux command. All right. Any other questions? Okay, so we'll kind of recap essentially what was part of the demo. So how do we secure the Kubernetes clusters? Well, firstly, don't panic. And your cloud provider has your back. So remember how we talked about Kubernetes being very complicated ecosystem, and it's hard to deploy it right. It's a headache basically to maintain. But a lot of that headache is taken on by the cloud provider if you went with the managed service. The third piece is the piece that kind of relies on us to do our due diligence and do our homework. So let's quickly walk through this. And this is kind of, it should be fairly aligned with what we've done in the demo. Firstly, the network policies. Network policies is a native Kubernetes way to restrict traffic within the cluster. It's not enabled by default in a lot of cases. So the some of the network plugins don't support network policies. And the worst part of that is if the network plugin that you're using doesn't support network policies, when you apply the network policy, you will not get any error messages because the network policy object will be created within the cluster, but there's nothing basically to enforce it. And that's the issue. So if you're not sure, always verify if the network policies work. And check if they don't, that essentially means that the CNI that either something's wrong with the policy or the CNI that you're using does not support network policies. By default, all traffic is allowed, even across namespaces. That's why I was saying namespaces are more of a logical segmentation unless you enforce some rules on top of it. And when you do apply network policies, try to apply least privilege and think about ingress and egress as well. That network policy editor is quite a handy tool. Probably if your policy is very complicated, you won't be able to use it, but kind of as a baseline, as a kind of point to get started with, it's a good tool to have in your back pocket. Rules in Kubernetes are quite interesting and flexible. They're based on labels, so you don't need to know anything about like IP addresses and where those pods are scheduled, et cetera, et cetera. You basically label your pods the way you want, and you can use labels either, and you can have multiple labels, but you can either say, okay, this is this application or this microservice, or this is part of, let's say, front end or the back end or the database. So you can either group multiple services, label specific services, and use all of those labels within your network policies to either say or define what the policy applies to, like what pods that it affect, or as a source or destination in the ingress or egress rules. For credentials, a big part of protecting credentials is those user accounts that are completely managed outside of the Kubernetes, and there's nothing new here from that perspective. So like, don't check in those credentials into source version control systems, and just generally protect them. Use MFA where appropriate. Use single sign-on so you deprovision your users, et cetera, et cetera. Then there's the instance metadata part. So that instance metadata potentially can be a huge issue, because imagine, like, if you don't do anything, imagine how it all works. You will have, let's say, a handful or several nodes that run your workloads. There's going to be different workloads running on the same node. And so if you assign some, let's say, AWS or generally infrastructure as a service credentials to that node, potentially any workload that's running on that node will also have access to those credentials. So those instance metadata credentials and roles and profiles need protection. Now, there's good news there. All of the major cloud service providers, Amazon, Google, and Microsoft, now allow you to map roles and permissions within their clouds directly to Kubernetes service accounts. What this means is you're not now grouping all of the workloads into one bucket and giving them same access as the whole node. You can say, this service account, which is mapped to this deployment in my cluster, will have these permissions within my cloud. So basically assigning those roles and assigning those permissions directly to the workloads. Those three major cloud providers, they all support them. They're called slightly different. Amazon calls them IAM roles for service accounts, IRSA. Google calls them GKE workload identity, and Microsoft calls them AKS Azure ID pod identity. But I think essentially that's a must to define, or at least to basically block access to any of the credentials from workloads if the workloads themselves don't need access within your infrastructure provider. Now, service accounts themselves, in most cases, your workloads will not need to talk to Kubernetes cluster. They have basically no business of doing that. They're not managing, generally not managing other workloads, not managing resources. So the best thing to do is disable that auto mounting of the service account token. If you cannot do that, then at least carefully review what permissions those service accounts have. Remember, every pod will have a service account. Even if you don't define it, it defaults to a default service account that's automatically provisioned within every namespace. It has a little bit of permissions, not a lot. So if you're not sure, just make sure you check it. And then, as we talked about, use your cloud provider identity management or any sort of single sign-on for your Kubernetes users and protect those. The next piece is control plane. So as you saw, all the interaction with the cluster happens through that Kubernetes API service. And from that perspective, that API service is a critical component of a Kubernetes cluster. So firstly, make sure that it's up to date, because from time to time, there are vulnerabilities that published in the API server. And if it's not up to date, you're basically exposing potentially your whole cluster through those vulnerabilities. Some cloud service providers make it easy. For example, GKE supports fully automated upgrade mode, so you don't even need to do anything. It just happens. And so you're always up to date with regard to the control plane. But second thing to think about is just generally access to the control plane. Again, all of the cloud service providers, many of them, if not all, by default will when they provision cluster, will make that API endpoint public. In itself, it's not a big issue because there's usually strong authentication with like certificates and private keys and all of that. But they do give you an option to limit network access to that API endpoint. So you can say only my corporate network has access, or only within the cluster you can have access, or only the subnets in the same cloud provider can have access to them. To the API endpoint. So if you're, I think it's generally a fairly good practice to just limit access to the API endpoint. If there's any issues, you're still protected by it. Kind of serves as an additional layer of the onion. The next part is securing workloads. So remember that security context that we've set to give the deployment or the pod privileged access. So security context can define rules for specific pods and specific containers. There's a lot of things you can do. Most notably, you can say this container is not allowed to run as root, and that's a best practice to not run your workloads as root. You can disallow privileged pods. You can disable privileged escalation. This was breaking my mind for quite a while until I realized that this is basically refers to tools like sudo, and basically tools that essentially can grant you like root permissions temporarily for whatever reason. So if you disable privileged escalation for a container, sudo will not work. It will basically break that that set UID kind of functionality within Linux. Disable host file system mounting. This should be best practice, not just from security, but from operational perspective as well, because like if you save something on, if you like mount a path on the node into a container, what happens if that container dies and is rescheduled to a different node? It will no longer have access to the same data that it was saving potentially there. So the generally bad idea, but even from security perspective as well, things like /proc /etc can contain very sensitive data that potentially can lead to privilege escalation onto the node from the container. And there's also this option of using read-only root file system, which essentially means that, okay, I'm starting this container and the core file system of that container is kind of frozen. You cannot write to it, you cannot download things, and only like things that I can mount as volumes from external storage will be read-write and maybe like /temp, etc. This just makes any sort of lateral movement, privilege escalation so much harder, because you land in a container, you cannot do like apt install or that npm install that we've used in the demo. So if you're lacking any tools, you cannot install them. If you want to write files and execute scripts, you cannot write files, and just makes attackers' life so much harder. So now these are the settings that you can set for specific pod, but there's also this mechanism called pod security that allows you to enforce some of these settings across all of the containers or some of the containers that you're running in your cluster. So there used to be a feature within Kubernetes called pod security policy. It's now been removed since, I think, a version 1.25 or something like that. It's been deprecated for quite a while. That allowed you to enforce, it was very flexible and allowed you to enforce these settings, but it was not very intuitive how to deploy, and a lot of people were getting errors or were not applying those enforcements correctly. So it's been deprecated. There's this mechanism, built-in mechanism called pod security, which essentially allows you to define, there's kind of 3 profiles or permission levels that are predefined within Kubernetes. They're called privileged, baseline, and restricted. Most of your workloads should run as baseline. Privileged allows kind of running privileged pods and things like that, and restricted is for less trusted sort of workloads. And you apply one of those profiles to the whole namespace, and any pod that's running in that namespace the profile will be enforced. So, and those profiles are essentially a combination of these settings. There's other versions of options as well that are kind of more flexible. And so there's the open policy agent, gatekeeper, kubewarden, Kyverno. So there's options there if you want to look into enforcing these settings on all the pods across the cluster. And the last thing with securing your workloads is keeping your operating system and kernel on the nodes up to date. To kind of, we've talked about the vulnerabilities in the kernel or the container runtime can lead to container escapes, and so keeping your nodes up to date can deal with that. Some of the cloud service providers can automate this as well. So for example, GKE can completely, fully automated keep your operating system on the nodes up to date. Pause for seconds, just for a minute. Sorry, pause for questions, just for a second. No questions. All right. There's just some additional items. So there's options that I know GKE definitely supports it. There's options for further container isolation. So GKE has this thing called GKE Sandbox. It essentially uses userland kernel emulation to provide even further containerization of containers or isolation of containers. There's other options there as well, and this is fairly developing field. So the cloud providers support more and more of these capabilities over time. Definitely look into securing your images. So that basically covers the supply chain part. So using only trusted images as trusted third-party images within your cluster, so that there's sort of less chance of something malicious sneaking in. Using minimal base images for your workloads. Minimal base images basically remove the number of things that can go wrong and the number of things that can have CVE that could affect your cluster. So the less stuff you have in the image, the better it is overall for maintaining and securing and vulnerability management specifically for the cluster. There's scanners that can scan images for CVEs, and I'll mention some of the open source tools with that regard in a couple slides. And just the general stuff, securing your code, securing your application, because that's one of the vectors, and a fairly common vector of how things can get into your cluster is by hacking or exploiting the workloads that you're running. All right. Yeah, and so we've talked about the static analysis of YAML files. So kubesec and kubetest are two of the open source tools, and major most of the commercial vendors that are in the space in the kind of container and cloud native security space would have their own options for static analysis of YAML files as well. All right, and some miscellaneous items. If you're using Helm, and chances are you are, it's very common, especially if you need to deploy some third-party components into your cluster. Either make sure that you upgrade to version 3, highly recommended, or at least make sure that you took care of access to Tiller using something like network policies. We should always think about logging. There's multiple layers of logging when it comes to Kubernetes clusters. One is the Kubernetes control plane, basically audit log of things that are happening within the cluster. But you would also need to think about logging for your applications and how you collect those logs out of all the pods and basically consolidate them and have them in one place for analysis and monitoring. And then protecting access to Kubernetes nodes. As you've seen, so node has credentials within the cluster that give the node, the kubelet specifically, quite a lot of access. And essentially, if I have access to a node that's part of the Kubernetes cluster, chances are I'll be able to escalate my privileges within the cluster. So controlling who has access to the nodes is really important. And ideally, nobody should manually logging into, like SSHing into nodes and doing things like that. And this is why it's really important to prevent those container escape type scenarios, because the access to the node is a very, very privileged access. One of my last slides. So there's this whole market for what I call, and I'm not sure if this is the official term or not, but I call them cloud native security solutions. These are essentially security solutions that are specifically tailored to monitoring and securing Kubernetes and cloud native containerized workloads and clusters. So generally what they do is they can provide cluster configuration validations, basically running CIS benchmarks. They can scan images for CVEs, either like all the images in your private registry that you maintain, or at runtime. So they'll basically check, okay, what containers are running, what images they're using. Let me check the CVEs in those images. And then they can provide container behavioral analysis. And this can be either rule-based or behavior-based. And this generally they tend to be quite detailed, meaning that they monitor all the processes that are executed, all the syscalls and file operations. So for example, if it's anomaly detection based tool, it can see that, okay, I have this pod running. Usually it only makes network connections to this endpoint using port 443. Now all of a sudden it's connecting somewhere here using a high numbered port. This is unusual, so I'll raise an alert and see what's happening there. So those kind of things. And rule-based, you can imagine things like, if I'm running an Nginx server and all of a sudden it spawns bash as a child process, that's an unusual situation that probably should be responded to. So that behavior analysis, those are the types of things that the tools monitor, and things like creating unusual files or making unusual syscalls or dangerous syscalls like mount and things like that. The fourth part is they often include cluster network traffic monitoring and or enforcement. This is kind of superficial on the enforcement part in a sense that there's already network policies, but the monitoring could be interesting from the perspective of those unusual connections. Or let's say you have this pod that's running and it generally only talks to other services within the cluster, but all of a sudden it starts talking to the API server, and that could be something that's indicating an attack and somebody doing reconnaissance within your cluster. And they can also provide forensics capabilities, like grabbing a snapshot of processes or process trees and syscall call trees and new files and things like that. So if you do have incident, you have as much information as you need to be able to investigate. I'm not going to name any vendor names. There's quite a lot of them. If you're interested, just reach out to me privately. I've got a Twitter handle that you can DM me on, and I'll be happy to talk about the possible options there. Okay, and now some of the goodies. All of these are open source tools. I've used not all, but most of them, and I highly recommend them. So Aqua Security, as you can see, they're doing quite a lot of open source work and kind of open sourcing a lot of the tools. And their tools, especially Trivi, which is the container CVE scanning tool, is outstanding. It's easy to use. It's getting you reliable results. But so Kubebench is a tool that that can run CIS benchmark against the cluster configuration. KubeHunter is somewhat similar, but doesn't focus on CIS benchmark specifically, just does a security assessment of the cluster. And you can run it either from sort of outside as administrator, in which case the use case will be somewhat similar to Kubebench, but you can also run it from within the cluster. So kind of simulate that attack scenario when somebody hacks into your workload and basically simulate what they can get access to, basically what we did during the demo. KubeScan is another kind of Kubernetes workload security assessment. So that's the thing that can scan for things like privileged containers and etc. And Falco is a runtime monitoring tool. It's maintained by a company called Sysdig. They have a commercial product built around that, but Falco itself, the engine, and some of the rules are open source, so you can run Falco to monitor. So that example where a bash shell is spawned by Nginx is one of the rules that Falco has as a built-in rule. Resources, I'm not going to talk about all of them, but one thing I want to mention is that first line. There's a free CNCF training called Introduction to Kubernetes that's very, very, very good. And I highly recommend doing that. That will give you like 80% of everything you ever want to know about Kubernetes and how it works, and kind of also will give you a little bit of hands-on experience. It's free. It's on EDX. Just it's free if you don't need like a certificate of completion. Go and check it out. It's a CNCF official training. It's very good quality training. The other kind of other resources, and I'll post all the links later on, but basically resources that can help you learn Kubernetes and learn Kubernetes security in general. The last one as well I want to highlight, OWASP has a Kubernetes security cheat sheet that's decent, so check that out as well. That's all I had for today. We ran for quite long, almost 2 hours. Oh my goodness.
That was quite amazing. That was most amazing.
That's my Twitter handle on the screen, airman604. Again, feel free to reach out. I'm always happy to chat Kubernetes security, and not just like product security, application security in general. Happy to discuss, happy to kind of connect you with some of the commercial vendors, or at least give you my jaded opinions on them.
Always like the real jaded opinions. Thank you very much for that. That was incredibly in depth, and I know I'm going to be watching, replaying, pausing, rewinding, playing that one again for quite some time, because it's always an ongoing, and so many organizations are working with it. There was one sort of comment / question that was left in terms of auto update, and that you know, from a security point of view, you can see the reason for doing auto update, but it was really the challenge of maintaining a production environment with auto update if there's deprecated APIs or deprecated third-party components or. And so that kind of stability and moving an update through a test environment, I could see it working, you know, auto updates in a test environment and then moving that to a production environment. And that's probably really the more pragmatic solution here, as opposed to having an auto update in production. That was one thing that was mentioned.
Yeah, a quick comment on that. I would check the settings on the auto update, and I can't remember off the top of my head, but I have a gut feeling that so Kubernetes supports several recent versions, like 1.22, 1.25, 1.24, that kind of thing. I think auto update only updates the most minor of the semver. So like it will update from 1.22.1 to 1.22.2, but will not update between those mid versions, but from 1.22 to 1.24. And generally APIs don't break things within the same kind of mid version. Yeah.
Usually.
But auto updates, yeah, there's always that balance. They go for auto updates, risking breaking things, or no.
Awesome. So we'll be continually watching this space. Check out OWASP Vancouver. There's a YouTube channel, I believe, as well. So I'm sure there's lots of good content there, and there's always the OWASP Vancouver meetups. And you recently just had the OWASP, I don't know, let me correct
AppSec Pacific Northwest.
Pacific Northwest.
It was a collaboration between Portland, Seattle, Vancouver, Victoria, 4 OWASP chapters. We did a full day conference. I'm not sure if it's published on YouTube yet, but yeah, it was just recently. It's our second one. We're doing them in June generally, and yeah, I think it was a good event this year.
Awesome. All right. Well, thank you again. We'll look forward to your next presentation to OWASP Ottawa in the future sometime, and watch this space. We'll be talking about our July meetup sometime, electrons willing, weather willing, because, and I keep saying this on this channel, I don't know what your 22 bingo card has, but I've sort of thrown out 3 by now. So thanks again, and we'll see you online.
Thanks, all. My pleasure.